Yeah, in the last module we looked at the concept of overall heat transfer coefficient. So, this is overall heat transfer coefficient, a very important concept which we will come across again in internal force convection as well as in heat exchanger, and in general wherever we want to combine all the effects into one single number. This is called overall heat transfer coefficient. UA is a constant. This is something you need to take back home with you, which is nothing but summation of the thermal resistances in total. This is important, and U by itself has no meaning. We will define this as U1 A1 is equal to U2 A2 is equal to U3 A3 is equal to da 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 da, da UN AN. If there are n surfaces, you can define one overall heat transfer coefficient for each particular area. In a plane wall, of course, none of this will change, because A1 equal to A2 etc. in a plane wall. Therefore, U1 equal to U2 equal to UN, whereas in a radial system U is not a constant, but U times A is a constant. That is what I need to see here. Okay. So, we looked at a cylinder, now we will look at a sphere. I am not going to go into the derivation of the heat diffusion equation for a sphere, but I am just going to write for 1D radial steady state no volumetric heat generation case, we will write 1 by r squared d by dr of k r squared dt by dr is equal to 0. This would be the simplified governing equation. So, simplified equation, heat diffusion equation in spherical coordinates, and k can come out. So, which is nothing but 1 by r square d by dr of r square dt by dr equal to 0. If you are talking of this, so you will see constant thermal conductivity k has come out, and then you will say this one integration d by dr of r squared dt by dr is equal to 0, which means I put here constant k, which means r square dt by dr is equal to C1. This is your first integration. Therefore, dt by dr is equal to C1 by r square. Unlike there where it was C1 by r, in cylinder you have C1 by r square. So, integrate again, T of r is equal to minus C1 by r plus C2 minus C1 by r plus C2. Okay. So, there you had a logarithmic relationship, you have here constant over r kind of relationship, and of course, you have two boundary conditions just like before. At r equal to r1, t is equal to Ts1, at r equal to r2, t is equal to Ts2, Ts1 greater than Ts2. When I put these two together and do the maths, so you will get Ts1 is equal to minus C1 by R1 plus C2, Ts2 is equal to minus C1 by R2 plus C2, subtract one from the other, you would get Ts1 minus Ts2 is equal to minus C1 1 over R1 minus 1 over R2. Therefore, C1 is equal to Ts1 minus Ts2 divided by 1 over R2 minus 1 over R1, 1 over R2. So, this is C1, and you substitute here for getting C2, you will get C2 is equal to I am not going to do the maths. You substitute this in either this or this. Any of these, when you substitute, you get C2 is equal to Ts1 plus 1 by R1, Ts1 minus Ts2 divided by 1 by R2 minus 1 by R1. Okay, once you do the maths, and that's all shown here in the slides. So, you have C2, you have C1, and you put all these together. I am not going to write this. You will get T is equal to minus C1 by R plus C2. I am substituting C1 and C2, C1 and C2. I am going to get the temperature distribution. It really does not matter. You do not need to remember any of this. The point to note is T1, TS1, TS2, R2, R1 are all constants. So, TS1 is a constant. This whole thing is a constant. 1 by R1 is a constant, only 1 by R is a variable. So, A plus B into constant minus 1 by R, that is the functional form. Okay. So, it is not linear, it is not logarithmic, it is some other form which is having constant minus 1 by R. So, if you take a spreadsheet and try to plot this, you will get the temperature distribution for a given set of problems. Again, just as we did in the cylinder, we are going to write the expression for the heat transfer rate. Q is minus Ka dt by dr. For a surface area of a sphere, we have A is 4 pi r squared. So, Qr is minus K 4 pi r squared dt by dr. dt by dr came from the previous page where we had the expression here. dt by dr is C1 by r squared. So, I will substitute from C1, which is this one. C1 is Ts1 minus Ts2 divided by 1 by R2 minus 1 by R1. I will substitute that whole divided by R squared is dt by dr. So, when I do the maths here, I am going to get Qr is 4 pi k into delta T divided by this. Again, it is independent of R. But heat flux, of course, Q by R 4 pi r square is strongly dependent on R. There it was 1 by R form, here it is 1 by R squared form, it is very strongly dependent on R. But the more important thing here, what did I say? Qr is delta T divided by everything else, that everything else is your thermal resistance. 1 by 4 pi k into 1 by R1 minus 1 by R2. This is your thermal resistance for conduction in spherical coordinates. Okay. So, this is something you should remember. Let me just go back and write this. R conduction in sphere is 1 by 4 pi k 1 by R1 minus 1 by R2. I do not remember it with too much effort. R1 is smaller, so 1 by R1 is larger, which means this bracket is a number which has to be greater than 0. Again, you have series and parallel combination. In cylinder, sphere, whatever you want to do, everything you can do as we did for plane wall. For example, I have a sphere which has a particular wall thickness. So, this is resistance is given by this. Then I have two materials which are providing insulation, one for the top half and one for the say the bottom half, like this, two different materials. Heat is going to flow two different paths across the same temperature difference. So, you would have resistances in parallel and series. So, this is your wall resistance, this is your insulation resistance, and this is the outside. Point is, whatever be the circuit, it is just a group of numbers which are going to sit together. So, this is the pipe, this is the wall, and this is insulation 1, this is insulation 2. So, you have heat transfer in parallel, one part here, other part here, which is there. Okay. So, that is what is exemplified by these. So, point to remember is the thermal resistance. Okay. Okay, a very simple problem is there. A thin walled metallic container is used to store liquid nitrogen at 80 Kelvin. The container has a diameter 0.5 meter covered with an evacuated reflective insulation. composed of silica powder, 25 millimeter thick, outer surface is exposed to ambient air at 310 Kelvin. Convective heat transfer coefficient is 20 SI units, latent heat of vaporization and density of liquid nitrogen is given. Thermal conductivity of silica powder is given. What is the rate at which liquid nitrogen will boil off? Very simple problem. You have liquid nitrogen which is inside this spherical container. It is at 80 degrees, 80 Kelvin, and heat from outside is going to come in because outside is at 310 Kelvin. Okay. So, because of this gradual heat coming in, there is going to be evaporation. So, if you allow heat to come in over an extended period of time, slowly the liquid nitrogen will evaporate. Okay. If you have a container which is sealed completely and you do not allow for evaporation, pressurization will happen. The liquid will become vapor and then the container will pressurize itself. So, you might want to avoid that, and therefore, you are allowing some vent, and the thin walled container has radius 0.25 and there is insulation which is of a particular dimension. Okay. So, it is a spherical coordinate problem. You have convection on the outside. This one is not flowing, the liquid nitrogen is not flowing. So, there is no H associated with it. It is just like a pool which is sitting there. Okay. So, if you are talking of water flow through a pipe, there would be an H associated with it. This is like a stagnant liquid. So, you are not being given any H. So, you have two resistances, one for the wall, other for the insulation. These are in series. You have a convection resistance on the outside. The Q is going to be between the cooler liquid and the warmer surrounding. So, 80 Kelvin and 310 Kelvin and 80 Kelvin, three resistances are going to be there, and we are going to see what they are. Liquid nitrogen is stored, find all these things, steady state condition, 1D heat transfer in radial direction, negligible heat transfer through the container wall and from the container, negligible resistance to heat transfer through the container wall and from the container to nitrogen. Why are we assuming this? We are assuming this because no information is given about the wall dimension. Okay. Thin walled, when I say thin walled, it just means that the resistance due to the wall can be neglected, we do not have to worry about it. Okay, that is why. Suppose the wall dimensions were given, inner and outer wall thickness and the thermal conductivity of the wall material were given, we would have to take that into account as an additional conduction resistance. Okay. So, here only two resistances, constant properties, negligible radiation exchange between the outer surface of the insulation and the surroundings. So, we have two resistances, one conduction through the insulation, other convection to the outside. Heat is flowing from T infinity 2 to T infinity 1, and we just need to calculate R T convection outside, 1 by 4 pi R outside squared times 1 minus R inside of the insulation minus 1 minus R outside of the insulation. That is what is given here. Convection on the outside surface area is 4 pi R2 square. So, H into 4 pi R2 square. So, put all this together, you put QR, everything is known, QR is 13.47 watts. And if you look at these numbers, 17.02 is the insulation resistance, convective resistance is very small. Insulation provides a good barrier for heat transfer. So, if I want to change something, I will change something here, 17 can become 20, it will be good for me. But making this 0.05 to 0.07 is not going to, even 0.1 will not have any effect. So, this is my dominant or controlling resistance. The conduction or the insulation resistance is the conduction resistance, which is the dominating resistance. I will change this even by a little, the effect will change. 17 becomes 18, I will have a smaller QR, whereas 0.05, even if it becomes 0.1, total is 17.07, instead it would become 17.12, hardly any change. Okay. So, that is something which you need to note, the scale of these two quantities, which is a dominant, which is a less dominant quantity. and that is because insulating materials have very low thermal conductivity. Here you have 0.0017 as the thermal conductivity. So, once you find the Q, Q is nothing but m dot HFG. So, it is we are writing E dot in minus E dot out is equal to 0 for the working fluid. So, QR is what is coming in has to go out by evaporation. So, m dot HFG is your Q out. So, 13.47 is m dot into HFG. So, m dot is 6.74 into 10 to the minus 5 kilogram per second, multiply by 3600, you would get per hour, multiplied by 24 hours, you would get per day. 5.82 kilograms per day of liquid nitrogen is lost, and if you want to write it in terms of the volume, volume is basically mass by density. So, 7.24 liters of liquid nitrogen is evaporated per day here, and the volume of the container is 65 liters. The daily loss is about 11.14% of its capacity. Now, this if 11.4% is lost, next day that whole space is going to be vacant. Okay, the container was initially full. Then if it's empty, there will be convective heat transfer there, and there will be additional sloshing and things like that. As the container, if it is moving, you would have the liquid level going up and down, thereby causing turbulence and thereby also increasing the heat transfer, etc. So, let us not worry about it, but the point is on a given day when the tank is full, 11.14% of the tank is going away as evaporation. Okay. Very simple concept now, based on resistances in series is what we call as critical radius of insulation. We know that insulation is a necessity to reduce the heat transfer. Okay, that is a desirable outcome of insulation. Since in a plain wall, if I keep on adding a thickness, I am going to increase the resistance and thereby the heat transfer is going to reduce. But if I look at a cylindrical geometry, if I look at the cylindrical geometry or a spherical geometry, plain wall, I keep this is L1, I have another resistance L2, I keep adding resistance. Summation of R total goes on increasing, therefore, Q will drop as resistance increases or thicknesses get added. But if I am having a radial system, this is my wall, this resistance is constant, this is my insulation. Let us look at a case where my insulation now has moved here, R insulation new, this is R insulation old. Ideally, we would expect that because of this additional increase in thickness, my heat transfer should go down. So, this is T hot and this is my direction of Q. Ideally, we would expect that, but what is happening? I have R conduction here and R convection which is there. Conduction is due to wall plus insulation. Convection involves area, surface area of outer wall, outer insulation, right. So, convection is happening from here, earlier convection was happening from here. Convection resistance is 1 over HA, surface area is more. So, A red is greater than A blue, therefore, R convection red is less than R convection blue, which means what? As I increase my resistance, as I increase my insulation thickness, convective heat transfer area goes on increasing. Okay, the surface area available for heat transfer goes on increasing, therefore, resistance to convective heat transfer decreases. R conduction through insulation increases, that is increasing. So, if I make a plot, conduction resistance goes on increasing as my radius increases, okay, convective resistance goes on decreasing. Therefore, summation of these two is the total resistance R total. There will be an optimum at which this would be a minimum, which means that would be the case where my Q would be the maximum, okay, or it could be the other way depending on what our application is. So, I will just go through this in our slides. You may want to be very sure what is the purpose. So, if I want to reduce the heat transfer or if I want to increase the heat transfer. So, both of these are important, and the point is the conduction resistance will always increase, the convective resistance will decrease, and depending on what is dominant, your heat transfer will either increase or decrease. So, that is what is shown here. So, you have a cylinder, you have the conduction through the wall remains the same. So, that has not been accounted here. So, T 1 minus T infinity divided by these two resistances. Now, those two resistances are going to play a different role, one increase, other decrease. So, if I want to maximize the heat transfer rate, so dQr by dR2, dR2 is my variable. I am changing this outer thickness, which means the R2 is my variable, dQr by dR2, you do the maths for this. T1 minus T infinity is constant, you just have the denominator which needs to be differentiated appropriately. You will get R2 will be where it is dQr by dR2 is 0, where the heat transfer rate is maximized. That radius is called as the critical radius. For a cylinder, it is going to be coming out as K by H, just a simple exercise for you to do. So, the graph of heat transfer is shown here. So, if I am on the left side of this, okay, if my bare pipe is here, if I am adding insulation till here, it is going to increase. Beyond that, it is going to decrease. But if I want my Q after insulation to decrease, I should cross this path. I should cross this corresponding path here, and I should be in this path so that my heat transfer decreases. Okay. So, we can't just add some insulation and say no, it is going to decrease the heat transfer. That will not be the case. We have to cross a certain thickness, critical thickness, beyond which the Q will actually decrease. So, critical radius of insulation, some more points are there. Make sure that the outer radius exceeds the critical radius of insulation. So, some explanation is there, depends on the thermal conductivity. So, if you are going to have radiation into consideration, H, if you add radiation, that would actually increase the H. So, K by H therefore, would be R critical would be smaller. So, critical radius of insulation taking radiation into account other than pure convection would actually be smaller. Okay. That is something you can try. Critical radius would be much less in forced convection. Why? Because H is larger. In natural convection, it is going to be larger because H is small. So, it is often less than 1 millimeter. Therefore, we can insulate hot water steam pipes freely without worrying about the possibility of increasing the heat transfer by insulating the pipe. So, the R critical is so small that even whatever little you do as insulation will be greater than that R critical. So, we do not have to worry. The radius of electric wires may be smaller than critical radius of insulation. Therefore, the plastic electrical insulation may actually enhance the heat transfer and therefore, keep the steady state operating temperature lower, and therefore, you are going to operate the wires safely without melting them. You can also do the same analysis for a sphere by writing the appropriate equation for conduction resistance of a sphere and the convective resistance. Do the differentiation, you can show that the critical radius is 2K by H, cylinder was K by H. Okay. You can do that. So, we have a numerical problem here which I will just do very quickly. So, this is 3 mm diameter, 6 mm, 6 meter long electrical wire is tightly wrapped with a 2 millimeter thick plastic cover. Okay. So, you have an insulation there whose thermal conductivity is 0.15, whose thermal conductivity is 0.15. That is the value of the thermal conductivity of that insulating material. Electrical measurements indicate that a current of 10 ampere passes through the wire, there is a voltage drop of 8. So, I is given, V is given. So, you know how much V into I, which is the power, which is the heat that is being passed through. From that I will get that. If the insulated wire is exposed to a medium at 27 degree with a heat transfer coefficient of 12, determine the temperature at the interface of the wire and the plastic cover. So, wire is there, there is a cover. What is the temperature at that interface in steady state operation? Determine whether doubling the thickness will increase or decrease the interface temperature. So, I have a plastic and a convection resistance. So, the two resistances here are, one is because of the conduction through the plastic insulation, other is the convection on the outside. The heat is coming in from the electrical heating, which is Vi, that is what is given here. You are asked to find the temperature at the interface of the wire and plastic, which is T1. Okay. K of insulation is given. So, R insulation can be calculated because dimensions are given, R1 and R2 are given. So, dimensions are given. Q is given. So, because Vi is known. So, Q is given. R convection outside dimension is given, H is given. So, R convection is given. So, everything is given, you can calculate the temperature. So, let us go through this. So, steady state operation, this is the first assumption. Heat transfer is 1D in radial, you have to write these things, you have to get into the habit of writing these things. Steady state, 1D conduction, okay, in radial direction, constant property is thermal conductivity, negligible contact resistance, and radiation effects if any are neglected, or you can say what is said here, heat transfer coefficient incorporates the radiation effect. So, at steady state, Q is equal to Vi, which is 80 watts, whatever is coming by generation has to be removed. We have the two resistances, one by HA2, which is the convection, HA2 is 2 pi R2L, and plastic insulation log R2 by R1 divided by 2 pi Lk. If length were not given, you would do it per meter basis, unit length basis, all the areas would be per unit length. So, you can calculate the two resistances, you know Q. So, T1 minus T infinity is known. So, T1 is the leftmost temperature, which is the temperature that we want, 89.4 degrees centigrade. We did not involve electrical wire directly in the thermal resistance, since the wire involves heat generation. Okay. So, heat was coming in, that had to be taken out. So, what is happening in the wire was not of consequence to me. Okay. Now, second part, what is the critical radius? If I have to double etc., what is to be done? Critical radius is 12.5 mm, which is larger than the radius of the plastic cover. Therefore, increasing the plastic cover will enhance the heat transfer. How do I know that? We are in this part, we are here. Okay. So, if we enhance, we add the thickness, we would enhance the heat transfer, and therefore, increasing the thickness will enhance the heat transfer until the outer radius of the cover reaches 12.5 mm. Rate of heat transfer will increase when the interface temperature is held constant, or T1 will decrease when Q is held constant. So, you figure out what is to be done, because if you are removing heat, T1 will decrease. Okay. And based on this, you can get a plot of temperature versus the radius or thickness of the insulation. For a 4 mm plastic cover, the temperature drops to 77.54 when the thickness of the plastic cover is doubled. Interface temperature reaches 71.14 when the outer radius of the plastic cover equals critical radius. How do I do this? I go and substitute the appropriate numbers into these values. So, radius is doubled, area will be doubled, appropriately R plastic would change, and therefore, Q is 80, you will get a new temperature. If you are at R critical, that would be a new radius, new R convection, new R plastic, new temperature. That is what is plotted here. If you do it for various R, again calculations have been done for R critical and double the radius. These are 2 points in this whole graph that is there. Okay. So, in the next module, we will look at plane wall with heat generation, and that should pretty much end our as part of convection. Then later on Professor Prabhu will look at extended surfaces, which is fins, and then unsteady convection. Thank you.